In this video, we're picking up from where we left off. We've established the hypotheses, and now we're going to look at the test statistic. Establish how do we find support for the alternative hypothesis? Does the data support this hypothesis? So we need to do a computation, and that is with the test statistic. The test statistic is going to allow us to assess the strength of our sample evidence in support of the hypotheses. I should say, in support of the alternative hypothesis. The formula for our test statistic, it is abbreviated TS. The S actually stands for sample, and T, well, we're going to be using the T distribution. This, you might remember a Z-score. This is essentially like a Z-score, but it follows a T distribution. We are going to compare two sample means, how different they are from one another. Technically, there's a -0 here because that's the hypothesized difference. If you reflect back in the null hypothesis, the null hypothesis states no difference, which is represented by a 0. But we need to relate this to the spread for the difference in means. So that is the standard error that we saw in chapter 6.7. So that's s squared over n for the first sample, plus s squared over n for the second sample. I'm going to defer to the text here to explain a little bit of this. Notice the structure of the test statistic. It is a measure of how far the difference between the sample means, that's the y bars, how far the difference in the sample means is from the difference we would expect to see if the null hypothesis were true. This is referring to the -0. Now we can just omit writing it, but it is a reminder of what is being tested against. And this is expressed in relation to the standard error of the difference. I'm going to put this formula in a box. We're going to use it all the time. Asterisk, asterisk. This test statistic is approximated by the T distribution. There's not just one of those. We need to talk about the appropriate degrees of freedom. There is the intense Welch-Satterthwaite method for calculating degrees of freedom, and that is most accurate. But we'll use the conservative approach just to be easy. The conservative approach for determining the appropriate degrees of freedom, we'll just use the smaller of the two sample sizes. So n minus 1 for the first sample, or n minus 1 for the second sample. Whichever one of those is smaller, go with it. Again, I'm going to look to the textbook to help explain some of the properties of this test statistic? It's just a number, right? Remember a z-score. And think about the empirical rule a little bit, if that's helpful. A z-score, within plus or minus 2 standard deviations, right? That's the center or the middle 95% of most distributions. A z-score that is like a 3 or a 4 or a -3, -4, that's quite a far distance from the center. So looking at the book here, if we got a test statistic of a 0, the only way that can happen is if the two sample means were identical, right? You don't get a 0 from the denominator. That's no good. You get a 0 from the numerator. If the two sample means were identical, doesn't that provide evidence in such that there's not a difference between the two means? That would be perfect agreement with the null hypothesis. But even if the null hypothesis were true, we would not expect any two samples to result in a test statistic of exactly 0. We would expect these sample means to differ from one another because of sampling variability. We've demonstrated sampling variability in lab. Test statistics near 0 are going to indicate that your data are compatible with the null hypothesis. Any observed difference can be attributed to chance variation. Well, what then would be considered evidence that supports the alternative hypothesis, that there is a difference? If there was a considerable difference between two population means, then we would expect that our test statistic would fall in the far tails of the t-distribution. It would be unlikely that if the null hypothesis were true, to observe such an extreme difference. And we can compute a probability for that chance. Let's do a brief recap. A test statistic near 0 indicates a lack of evidence for the alternative hypothesis, because the alternative hypothesis states there's a difference, and if a test statistic was near 0, that's supporting no difference. Our conclusion there would be what's called, or what's stated as, do not reject the null hypothesis. A large, I'm putting it in quotes because we still need to discuss what small and large is. A large test statistic provides evidence or support for the alternative hypothesis, or it is unlikely that the null hypothesis is true. Here, we would state a conclusion that is written as reject the null hypothesis. Okay, so we've talked about establishing the structure of the null and alternative hypothesis. We've looked at the formula for the test statistic and how we state conclusions in a very statistical, technical way. But what we have not talked about was the p-value. We'll do that in the next video.